All right, let's take a look at the harmonic oscillator. Now, just for recap, let's do recap up here. Just for recap, conceptually, let's think of the spring. Let's say you had some sort of spring attached to a wall, to some ball. Just say there's a little bouncy ball there. Somehow got attached to a spring. This can oscillate back and forth. You know, you've got Hooke's law, right? Negative. Oh, I'm embarrassing myself. I don't even remember this very well, but some sort of force, spring force constant related to. I think this is Hooke's law. Related to the distance which it is displaced. Similarly, in a similar vein, sort of, you can imagine that this frequency, in quantum mechanical terms, it's related to the k over the mass under the square root. So keeping that in mind, keeping in mind this oscillation, this can go back and forth, back and forth. We can imagine, we can almost imagine that this occurs for some sort of, let's say, some sort of molecule. Let's say, oh, I don't know, let's say N2. For N2, you've got N and N connected, by some bond. Now, this bond, it's not fixed. I mean, these two don't fly off because they have a bond, but it's not stationary. This distance, this radius, it's called little r. This distance r of N1 and N2. It's not fixed, Just like on a spring, it can move. These guys have a lot of energy, These guys are moving crazy fast. You don't even see. But they're moving pretty fast. So these are bound to stretch and vibrate and oscillate. The harmonic oscillator will describe this state. We'll get into the nitty-gritty of it in a bit, but let's first see where it breaks down. So where the harmonic oscillator approximation no longer works is when it's far away from this equilibrium distance r, called r sub e. When these two guys get farther away from each other, and this potential function gets less and less parabolic, this is where this begins to break down, in this region, where ideally you would have a parabola, but you don't get this part. So here is where this approximation starts to deviate. This bottom of the well examples are sub e, that's your equilibrium bond length, and then as you get away from that, this harmonic oscillator approximation doesn't work. So knowing these first couple three states, energy states of the harmonic oscillator are helpful. So at the n equals 0 state, it's just a sort of no nodes, doesn't have any nodes, sinusoidal, and if it's one node, and this is actually a mixed state where you combine these two, you get some sort of, these two halves combine together constructively, and these two destructively. So you actually get a smaller hump here. remember correctly, the psi 2 n of 2. I think you actually have this has 2 notes actually, yeah, something like that. All right, and so that's the harmonic oscillator. One more thing about operators. You can have the two main types of operators we'll be talking about are angular. You can have 2 types of angular momentum operators, L squared and L sub z. Now, interestingly enough, these two are interchangeable. The operators are interchangeable. If you had L squared on some sort of state, you can interchange this with Lz. Now, what are these equal? When you apply them, when you apply L sub z to some state, you get M sub j h bar. If this, same thing if this were on the rotational, this would just be M. You can also apply the L squared operator, and you'll get j state times j plus 1 parentheses h bar squared. Remember, this is the state, this is the momentum. One final note for the midterm review is this concept of the frequency of light needed to excite some sort of molecule, to excite electrons. The initial energy plus the energy of the photon will yield final energy. So, rewriting this, you can envision, I'm sure you've already done this, will equal the final energy minus the initial energy. And because energy, Planck's equation, where this is frequency. And if this was a rotational, for rotational energy, I believe it is something like J plus 1, and then you have 2I here, I think, something like that, and then another J here, something like that. But anyway, you can see what I'm getting at is if you have, this energy will be at some state. This energy will be at some state. Some state of J initially, right? And then at final, it's going to be at a different J. So if you just take the differences, O and I, it's a moment of inertia, by the way, it's mu r squared. That's a mu. That's supposed to be mu. Let's rewrite that. It's not messy. I, moment of inertia is mu r squared. And you input that here. Don't quote me on this for the rotational energy. It's just something like it, similar to this. Actually, so I don't steer you wrong, I have should have the equation here. I'll probably edit this out so it doesn't look like I don't know what I'm doing. You can't see this right now, but I am absolutely frantically trying to find this. Oh, and it was behind me. It was behind me the whole time. So yeah. Oh, look at that. Haha, look at that. Okay, you see that? No alterations, right? And look at this. Energy for rigid rotor. H bar squared over 2I j plus 1. Do you see the similarity here? Let me zoom out. Can you see the similarity between these two? Oh. That's not very good juxtaposition, actually. Let's do it like this. Yeah, okay, anyway. Not tooting my own horn for remembering something that'll be on the equation sheet anyway. Selection rules. For rotational spectra, J goes to J plus 1. Rho vibrational, you have two types. You have, for both of them, V plus 1. But then their differences begin here with the J state. You have J plus 1 for the R branch and J minus 1 for the P branch. So that was that. We learned about the L squared and LZ operators, how they function. You can, oh, I forgot to mention this, but you can combine these with, you combine them when they have different M sub J's. And if they have different J's and if they're normalized, then it's okay too. Oh, there might also be some questions about, spatially, does this look the same like another kind, but we're not going to worry about that. Frequency of light to excite, selection rules, and the harmonic oscillator and where it breaks down and what the first couple of states look like. That's that.